Is it working? Yeah. So I'll talk today about this spectacular merger event in ABL 3411. So here is the list of like people involved in this project. So here is just like a brief summary of what I'm going to talk about. So I'll start talking a little bit about galaxy clusters, since not everybody is totally familiar with galaxy clusters here. And then I'll talk about ABL 3411, and then jump to the conclusions. So cluster of galaxies are the upper limit of the halo mass function. The total mass is like 10 to the 14, 10 to the 15 solar masses, and they extend to megaparsec scales. So they're basically composed of dark matter, like 80% of their mass is dark matter, and then we have like hot baryons, like 15% of the mass in the form of hot baryons, and then we have cold baryons in the form of cold baryons that are 5% of the mass. So the cold baryons are in the form of stars in galaxies and in the intracluster light, and the hot baryons like are the diffuse gas that is shock heated to 1 to 10 keV in the process of collapse of the cluster, due to the fact that they have very low density, 10 to the minus 2, 10 to the minus 3 particles per centimeter cubic. The ICM is optically thin and is also in a state of collisional equilibrium between electrons and heavy ions. If we think about the emissivity of this gas in the 0.1 to 10 keV band, it's mainly like due to a continuous emission because of the Bremsstrahlung, like the free emission, like electrons being scattered by the heavy ions. And also we have the addition of some lines due to K and L shell transitions in the heavy elements such as iron and oxygen. One way of detecting galaxy clusters is via the Sunyaev-Zel'dovich effect. So in 1972, these folks here, like they wrote like very nice paper, very well cited paper. So they claimed that the low energy CMB photons traversing a cluster of galaxies, should be inverse Compton scattered, and the photons of the CMB traversing the ICM should be inverse Compton scattered. So if we think about the low energy limit of the Compton scattering cross section, we can approximate by a Thomson cross section, and using this simple, like the first simple, so this simple equation right here, we can estimate the optical, the scattering optical depth of the ICM to the CMB photons. So we have like 10 to the minus 2. That means that one photon out of like 100 will be Compton scattered on average, and on average, the fractional energy gain will be like 1%. So combine the two effects, we have 10 to the minus 4 here for the Sunyaev-Zel'dovich effect. And if we think about the CMB temperature fluctuations, we have like typically 10 to the minus 5 fractional fluctuations in the CMB temperature. So in theory, it should be easy to detect a cluster of galaxies, since the effect is 10 times larger than typical fluctuations in the CMB. And that's what I show right here. So this is like a very nice, simple animation showing how we can detect cluster of galaxies. So below 217 gigahertz, we have a decrement in the fractional flux, and above 217 gigahertz, we have an increment. So looking for these decrements and increments in the CMB, we can search for galaxy clusters. And that's what Planck did and found in 2011, like the galaxy cluster ABL 3411. So this cluster is located at redshift 0.17, so not very far. When we look with radio telescopes at this cluster, we see very large extended halo emission, which is basically due to shocks and turbulence in the ICM, which is like an indication of a merger event here. Also, when we look with X-ray telescopes such as the Chandra, we see like surface brightness discontinuities, which is also like indication of a merging scenario. So here I present like our new data on the Chandra data on this galaxy cluster. So we have 215 kiloseconds of ACEs on this cluster. So 50 kiloseconds was obtained by HRC GTO time by Steve Murray sitting here. And then we have 165 kiloseconds, whose PI is Reynolds, also sitting here. So we have 215 kiloseconds of observation on this cluster. I'll try to show a little movie here. Let's see if that works. Oh, sorry. So this is basically the temporal evolution of the Chandra observations of this cluster, so as the photons arrive. A very simple thing, like just to show how the image was formed. So that's the image we have right now. So let me go back there. I can really see now. How do I put it? Is that the one? Why did I show that video? Anybody know where I should click to come back to the presentation mode? Oh, you screwed my talk. So where?
Yeah. Keep going.
The last one.
That one?
Yeah.
Okay, I'm sorry for the video. Okay, so here I have on the right image in the right plot, the right panel, we have like the C-smooth image of this cluster, just to highlight some of the features. So we have like this very nice cold front, like we see here. We have like stripped gas, cold gas. We have like some clump, X-ray clump in the south here. So this cluster is like has several interesting structures. And when we look at the surface of brightness towards the cold front right here, that's what we see. So beautifully described by beta model plus a power law. And if we look farther away, we can see what is an indication of a bow shock right here. So assuming that this is a merger, assuming that this is a shock, because we don't have enough counts to constrain the temperature in the upstream region. So assuming it is a shock and relating, so we can model the density by two broken power laws with a compression factor, and we can relate the compression factor to the Mach number. So that's what we get, basically, like very low Mach number, 1.32. And if we look here at the temperature, like that's so we have like a density jump by 1.94, a factor of roughly 2, and that's roughly the factor that we have here in temperature. So basically the pressure is roughly constant across the cold front. So no temperature, no pressure jump here. And just changing subject now, like talking about radio relics. So radio relics are just very large, elongated structures seen in radio that we find usually in the outskirts of galaxy clusters, merging galaxy clusters. So the idea is that these pre-existing electrons are reaccelerated by the shocks, causing them to emit radio in the radio band, and in a very, so this is the main idea, but this is also like a complication in terms of the efficiency of low Mach number shocks. So either you need like a pre-existing population of electrons sitting there, and when the shock traverses this region, like it boosts the energy of electrons, causing them to emit via synchrotron emission in the radio band, or you need some additional mechanism. So there's this very nice paper by Chini, Lorenzo, and Hamesh from last year that they claim that they have like this new mechanism to explain that. So basically the electrons bounce between the shock front region and the upstream region, but the difference, like the electrons going away from in the upstream region, they generate they self-generate a magnetic wave that bounces some of the electrons back to the shock front, and they gain energy via drift particle acceleration. So that mechanism will be capable of explaining the radio observations that we have of like relics. So, and here is the case of a Bell 3411. So we have like this beautiful relic, and using like symmetry arguments, like when we look, let me skip that. So when we look at the galaxy distribution here, so we have like two peaks in galaxy distribution, roughly consistent with two galaxy clusters with similar masses, 7 times 10 to the 14 solar masses. So this is a 1-to-1 merger ratio. The radio velocity difference between these two peaks is consistent with 0, meaning that we have like a merger on the plane of the sky. So using arguments like symmetry arguments here, we would, although we cannot really constrain the Mach number in the southern part, we can argue that it must be similar to the one that we measure in the north, since like it's a 1-to-1 merger, and we don't have any projection effects on this galaxy cluster. So just to conclude, like this is a very interesting galaxy cluster because we have this huge formation, this huge relic sitting right here, and using like arguments of symmetry, we estimate that if there is a shock in this region, it should be low Mach number, and it's good. It's a very good, interesting case to study like the efficiency of low Mach number shocks to create these giant relics in cluster of galaxies. Thanks.
So we have time for one or two questions.
Yes, quick clarification on the pressure balance or quasi-balance that you put up. Because I'm not really sure that this is what you should expect across a shock, right? Even like a moderate Mach number. First of all, by pressure you mean thermal pressure, right?
Yes, yes.
There's no RAM component to the pressure that contributes. So I would expect that with the addition of the RAM pressure, then there should be a balance. That's what the shock does. But the thermal pressure itself should not be balanced between the upstream and the downstream. This case is close to be balanced because it's very low Mach number. But I was wondering whether you can confidently say that this is exactly the same, or like what's the uncertainty in the?
Oh no, the uncertainties here are large due to the numbers that we get for the temperature and the density. Like I don't think we have the level. We cannot distinguish.
So it's like 50% off. Is that not compatible with what you see? Or?
No, so
The cold front and not the shock.
Maybe I'm
yeah. The cold front, like the cold front, is what I showed before. Let me go back.
Okay, no, this is probably yours.
Yeah, here. So I was talking about the cold front. This is like the. So sorry, that was the cold front. So the cold across the cold front, the temperature is roughly constant, but not the shock.
And in the meantime, let's do the switch between.
I just have a quick question. whether or not there was a BCG at each of the two peaks of the galaxy densities.
So one of the peaks here, and then we have like this image here is not the Reynolds knows better, but we have a star right here, right? That is causing a lot of complications. But here, like the peak is around here, and then yeah, we do have yes. But in the north, like there's a star in the field that.
No, there's a BCG there.
Yeah. Okay.
Okay, thank you.
And sorry for the confusion with the video. I don't know anymore. So there's this too. Probably this is yours. I think so. I'm sorry.
It's okay.
What to do? You should move to the other. Like this. Okay?
Oh,
And
okay.
and then you come here and. Okay.
All right. Okay, is this working? Yes. All right. Hi, so I'll be talking to you today about a survey that we're undertaking called COBRA, the High Z Clusters Occupied by Bent Radio AGN. And here's an example object from this survey, so you can see the idea behind what we're doing. So at the center of this image, you have a host galaxy and a luminous radio source that's bent. So there's an AGN there at the core. And you would normally, if you had an AGN like this that's isolated and it has jets and lobes coming out, they would come out relatively straight. But if you embed that within a cluster of galaxies or a group of galaxies surrounded by a bunch of gas, and there's any relative motion between that host galaxy and the surrounding gas, you get those jets and lobes bent. Okay, so that's what we're seeing here. So the background image is a Spitzer 3.6 micron image, so infrared. And then the radio source is from the VLA first survey. So it's a signature, again, of a cluster being there. When we went to observe this target, we didn't know there was a cluster there in the first place. We just had this radio source from the first survey, and we said, oh, we see this radio morphology. That means there should be a cluster there. We can see these radio sources easily to very high redshifts. So let's follow up with Spitzer. Let's see what's there. We expect to see a cluster. So that's the idea behind this survey. Pick out a bunch of these radio sources that look like this, that should be in clusters, and then follow up on them to find them. Okay, so here are my collaborators on this work. They include a number of current and former students at BU, including Josh, who's right there. I'll talk about some of his work, and also some other people here. Okay, so we know that radio sources in general, driven by AGN, you can find them in clusters. You find them in clusters at a range of masses and a range of redshifts. And we know that they have an important effect on the formation evolution of galaxies through AGN feedback. So, for instance, if you do cosmological simulations and you look at galaxy formation over time, and if you don't include the ingredient of AGN feedback, you end up having too many massive galaxies present day. So AGN feedback serves to sort of quench star formation, limit the masses that galaxies can have. And as I mentioned, certain types of radio sources, and we do a morphological selection, are preferentially associated with clusters, and so we can use them as beacons, as tools to find clusters that are otherwise difficult to see. Okay. And this is useful. You know, we're still always trying to find higher redshift clusters. We have tons of them at low redshift, but as you get above 1 or 1.5, we have many fewer. And one thing that's interesting about this sample is that it selects sources at a range of masses, where most cluster surveys have sort of a mass limit. Here we'll find groups as well as rich clusters at a range of redshifts. And by the nature of their selection, they all have AGN, so they all will be undergoing AGN feedback, presumably, so it provides a sample where we can study that at a range of redshifts. Okay, so just some background on different types of double-lobed radio sources, and I'll be talking a little bit about FR2s, FR1s. This is the old Fanneroff and Riley classification back from the 70s, where the FR2s are the classical collinear radio sources that are edge brightened. And then the FR1s are edge dimmed and overall generally lower luminosity than the FR2s. Specifically, we see on the right a subclassification of an FR1 is a watt or wide-angle tail source. Basically an FR1 type source that's bent in this characteristic C shape like the one on the front slide. And there are some other more specific definitions that go into making something officially a wide-angle tail versus a general bent source. I'm going to kind of lump those together and just talk about bent sources in general as being signatures for being in cluster environments. Because again, you need to have something doing the bending. If you just have an isolated source with jets, lobes, they'll tend to remain kind of straight. So it's a signature, there's some surrounding gas, and there's some relative motion that's creating that morphology. Okay? In terms of the kinds of clusters that we might find these sources, so they're arranged. Sometimes they're in very large scale, classical head-on mergers, like it's shown here. This is Abell 562. On the left is an optical image, and you can see at the center there's two very luminous elliptical galaxies there, left over from a massive merger. The contours are X-ray Chandra emission of this source. On the right, zooming in a bit, you see the Chandra emission in the color, and then the radio contours superposed. And the idea with this is so you have the X-ray emission elongated in this orientation with the idea that if there's a large-scale cluster-cluster merger, the gas has motion sweeping this way that's going to push back the radio lobes. So that's one way that you can get that kind of structure in the radio. You can also, turns out, get these types of radio sources in clusters that are relatively relaxed on large scales, especially if they have sloshing going on in them. So this is Abell 2029. It's a very well-known sort of canonical relaxed cluster of a galaxy. It's a cool core cluster, very well studied, very rich nearby cluster. On the left, you see it in the X-ray. The X-ray emission looks very smooth. On the right, you see the corresponding optical emission. This is what happens if you subtract off a model of the average X-ray emission and look at the residuals. If you look at the residuals, you see this sort of spirally structure here in the X-ray gas, and this is zooming in the center here. This is a signature of sloshing. What happens with sloshing is that you also have some kind of merger early in the history of the cluster where you have maybe just a group or a not very massive cluster coming by and interacting with this main cool core cluster. What happens is that the cool core, dense cool core gas is attracted towards that interloper. And because the interaction is off axis, it imparts some angular momentum, and so the gas sloshes towards that merging object and then sloshes back towards the core, and it traces out this spirally structure. And signatures like this in the gas can persist for many billions of years, so they can hang around for quite a while, and we can still consider clusters that have those types of signatures as relatively relaxed. So you see here on this relatively relaxed cluster, in the core, here's the radio source. Again, it looks like the C shape. There's bending of the lobes because the gas is flowing in this sloshing spiral to bend it. Okay, and here's another view. Looking at some more recent data of 2029, you see the very large spiral sloshing feature, one of the largest seen to date. And zooming in, you can see how it looks like it's probably causing the bending of the lobe. Given some assumptions of the content and flows within the jets and lobes here, and given the measurement of the pressure in the X-ray, we can actually constrain the velocity of the sloshing gas, and we get something like a couple hundred kilometers per second, which is consistent with what you get from simulations with sloshing. Okay, so that's the setup, and then we're going to look at some samples of these objects, again, to see what kinds of environments these things are in. There's a number of reasons we care about that. If we're going to do a big survey using these radio sources to find distant clusters, we want to know what we're getting into. Are we only going to find really highly disturbed clusters? Are we going to find sometimes relaxed clusters? Depending on what we want to do with the clusters, it matters. So if we want to do, say, cosmological tests using a gas mass fraction method that you can do with individual clusters, you don't need a complete sample, but you want those clusters to be relatively relaxed to do that well. So it matters that we're selecting clusters like that. So this is a sample from Ned Belgas, who's one of my former students from his dissertation, and he looked at a bunch of objects from the Chandra archive that had these types of radio sources in them, and went through and basically determined a number of characteristics of these objects to define them as being cool core relaxed clusters versus mergers. And he did this analysis also on a comparison sample of known relaxed cool cores and known disturbed merging clusters. So all these characteristics at the top are sort of markers for cool cores. This is like, for example, a temperature profile that declines in the middle is a cool core, short cooling time in the middle, a sloshing spiral signature, which you get with cool cores because you need the cool core to do the sloshing. So this is the comparison sample of cool core clusters. And so reassuringly, most of them have all or most of those properties. If you look at non-cool cores, again, reassuringly, they mostly don't have those properties. If you look at the wide-angle tail clusters, you see a mix, okay? So you can see here's Abel 2029. It's definitely a cool core. Something like this, definitely a merger. And then there are things all in between. So again, we're going to find this mix of different types of clusters. You can actually get some prediction on the types of clusters that we'll find looking at some properties of the radio sources themselves. So this is a plot of the central pressure in the X-ray versus the flare radius in the radio. So the radio jets come out sort of collimated and they flare, disrupt into lobes. That happens at a smaller radius when you have a higher pressure environment, as you might expect. Okay, so the lobes or the jets get disrupted closer to the core when you have higher pressure gas. The color here, this blue means a cool core cluster, cyan is a weak cool core, red is a merger. So this would suggest if we want to pick out cool core clusters, we would look at radio sources that have short flare radii. You can also look at it, correlation to the overall linear extent of the radio source. It's less of a strong correlation, but it's still there, that the ones in the cool cores from this sample have smaller linear extents. Okay, so this now is Josh Wing's work from his dissertation. Another thing that we did, I should probably hurry up too, was to correlate a large sample of these bent double sources with the Sloan survey to look at their optical environments to say, if we're trying to find clusters, are we really best off looking around these bent sources, or could we just look at any radio source? Could we look at straight ones? We're sort of assuming that this is a good idea, but let's go through and verify that. So we have these different samples, include a couple different bent radio source samples, a comparison straight 3-component sample, and a comparison single component radio source sample. Okay? This shows, matching with the Sloan survey, the distribution of redshifts for the host objects. Okay, so you can see most of them are down here, and they're sort of regular elliptical galaxy hosts. Most of them aren't quasars, but some of them are. That's what these are. Okay, so they have big emission lines, so we can actually get the redshifts from Sloan. Most of them are here. So important thing to note is that if it's an elliptical galaxy above about 0.7, we're not going to detect it in the Sloan survey, just due to the limits of Sloan. Okay? I'll skip through some of this, but we can break down the host properties, whether they're quasars or elliptical galaxies. We can divide them into FR1, FR2s, and here are some examples of bent and straight sources that we used, FR1 versus FR2. And basically, these are the results. If we look at the percentage of sources in clusters as measured by some overdensity within a 1 megaparsec radius region, we find basically the bent ones are more often in clusters than either the straight ones or the single component sources. So this is going to be an efficient way, compared to just looking around any radio source, for finding clusters. Okay, and here's an example of an object that's in Sloan at a redshift of 0.25. So here's where it gets more interesting, is that we have a number of sources like this, 653, where you have the radio source there. So this is the radio source superposed on the Sloan R-band image, and there's nothing there. Okay, so that means that that's a good candidate for being a high redshift cluster. Down here, a couple examples. There is something there. These are quasars. Okay, so you do see the host, and for these types, we do have redshifts, but most of them look like this. Okay, it's very efficient to follow these up first in the infrared to identify them as clusters, just looking at how magnitudes go as a function of redshift. This is 4.5 micron, the infrared's efficient. So we did that with Spitzer. We had a snapshot program, looked at 653 of these. Again, most are probably elliptical galaxy hosts. 33 are known quasars where we have the redshifts. From this survey, we've identified about 300 new cluster and group candidates with redshifts above 0.7, because again, if they were below that, we would detect them in the Sloan. Observe them all at 3.6 micron and some subset at both 3.6 and 4.5. The limit we'll reach is about m star plus 1.5 at a redshift of 1.5. Okay, so here's the high redshift COBRA survey. So we'll sample a range of objects 0.7 to 3. The upper limit is given by actual measured redshifts from a couple of the quasars in the sample. Again, wide range of masses, groups to cluster scales. All of them have AGN, so we can examine feedback at that range of mass scales and redshifts. Okay, so using the Spitzer data, we get a good idea of a clusters there, just looking at the overdensity of the number of objects. But we're following up also optically to get a better measurement of the redshifts. Then we'll want spectroscopic and we'll want X-ray eventually. So those are the steps we're going through. This is showing I band minus 3.6 micron versus redshift to give you an idea that even if we have just a couple bands with our images, that we get some decent idea of the redshift. Okay, so back to our examples. So here's what some of them look like with the follow-up observations. This is SDSS R-band. Don't see anything there. That's a star. And this circle is about a 500 kiloparsec radius in this case. Look at the Spitzer, and you can see a very obvious cluster popping out there. And then we have a deep I-band image from the Discovery Channel telescope that we've been using for a lot of these observations. You can see the cluster there clearly. This one's at a redshift of about 0.7. Here's another clear example, redshift about 1.1, an unfortunate foreground star. Here's the cover one, redshift about 1.4. And here's one that's a quasar where we have the measured redshift of 1.8. So these redshifts here are estimated based on photometry. This one's spectroscopic based on the quasar. Okay. Here's an example of one that was observed with Chandra. This is a proof of concept. It's not a very deep observation. It's only 20 kiloseconds. So the blue is the Chandra detection. Background image is a Spitzer image. And then you can see the radio contours. And then a number of galaxies that are circled and are thought to be cluster candidates based on their colors. And then the ones, I don't know if you can see, with the thick yellow lines are ones that have spectroscopic confirmation from Keck as being cluster members. So we have a little bit more detailed information on this particular object at redshift 0.96. So it's 10 galaxies with spectra. So from that, we can calculate a velocity dispersion, about 500 kilometers per second. We can measure the X-ray luminosity, a couple times 10 to the 44 ergs per second. So it gives us an idea of the kind of thing that we will detect in the X-ray going forward. But again, we have, much wider range of redshifts than what's shown here. Okay. In terms of looking at the fields as a whole, so this is work by another student, Rachel Paterno-Mahler. So the black histogram is showing the distribution of the COBRA fields, so our bent radial source fields, looking at the number of objects that we count up in the Spitzer images within a 1 arc-minute radius region, okay? So the ones over on the right, those would be fields that have a lot of sources, ones over here, ones that don't have a lot of sources. We compare that to a background survey field. We use something called SpUDS. It's a JEAT survey about 1 degree on the side, done by Spitzer. And so you're going to get a range, just randomly, a range of densities in those 1 arc-minute radius regions from a background region. So we fit a Gaussian to the lower half of that distribution of the background sources, because you expect even in a 1 degree field, you're going to sometimes get some groups or clusters showing up. Okay, so here's a Gaussian fit. So this gives us the mean number of background counts. And then we look at, these are our candidate objects over here. So this line is marking when we have 10 or more excess objects above this mean. Okay, so these are sort of the candidate objects out here. This is looking at, so we've also done this, so that's within a 1 arc-minute radius region. We've also looked at it within a 2 arc-minute radius region. Sometimes the radio source is maybe not right at the center of the cluster, so maybe we want to expand our radius. Sometimes maybe it's in a more compact or a more extended cluster. So we looked at it in both ways. So this would be if there is no excess above the mean, that would be here. So anything below here is actually a negative. And this would be equal. So everything up here is at least some excess above the mean. But we draw these lines to mark our candidates being things up here, excess of 20 sources within 2 arc minutes, or here, excess of 10 sources within 1 arc minute. So that together, if we include all of those objects, that gives us 282 radio sources from our sample of 653 that appear to be in cluster or group environments. So those are the ones that we're focusing on for our follow-up efforts. Okay, so the buzzer went off, so I'll just conclude. So the main idea, again, is that we have this large sample of bent sources. We've gone through the work of looking at their environments in detail at low redshift in the X-ray, in the optical, to see what we're getting into if we use these as targets for high redshift clusters. This is a cluster finding technique that's complementary to others. It's obviously not a complete sample. We can't use this for looking at the numbers of clusters in general versus redshift. So it's more looking at individual clusters, gas mass fraction in the X-ray, looking at galaxy evolution, properties using infrared or optical measurements, looking at feedback in different environments, different masses, different redshifts. And they may be objects that have large-scale mergers going on, sometimes relaxed objects with sloshing. Another thing that's intriguing is that they may also sometimes trace out large-scale filaments. So if you have a cluster here, merging along some filament, you could potentially have a bent source there too. You just need some flow to create the bending. And you could see that they certainly were not all in very rich environments. So the ones in poor environments are also interesting in their own right. All right, thanks.
So in the case of ABEL 2029,
Yes.
how do you distinguish between the gas movement and the galaxy movement there? Because the galaxy should be moving a little bit due to this motion, right?
Yeah, I mean, you can, right. I mean, and that goes into the uncertainty. I mean, you can say something about the velocity dispersion based on the spectra, but obviously that's the line of sight motion. So we don't have any direct measurement of how the galaxy is moving in that way. So yeah, I mean, that goes into the uncertainty was a factor of 2 in that measurement.
Put an upper limit to the velocity of the galaxy because it should be small since it's a BCG sitting in.
Yeah, so you can infer that it shouldn't be very large, and it's overall a very relaxed system. So, yeah.
Okay, thank you very much.
Okay, thanks.